All right, so for synthesis, there's a few different strategies that people use. I'm going to present kind of a hybrid version of what Klein presents in his textbook. He gets a little, I don't know, I think a little scattered in his presentation of how to plan a synthesis, so we're going to try to do it using a slightly modified technique. So there's a couple things to do before working on synthesis problems. So let's write these down. So before starting a synthesis, there's one thing that's very important, and some of you saw this on the exam. So you need to keep track of carbons, right? You can't gain or lose a carbon magically unless you've got some magic Orgo dust in your pocket. So determine if number of carbons has changed. Oftentimes in synthesis problems, there will be some sort of guidelines as to where you can start. It'll say you can start with any reagents that are 2 carbons or less, or 4 carbons or less, or it will even give you a starting material or reagent that you have to use, and then you have to go from there. But you need to account for all of your carbons during the synthesis. Don't gain or lose one on accident. In this case, if you gain a carbon, we know a couple ways to gain a carbon. What's the main way we know?
Methyl and iodine.
Yeah, any sort of alkylation, right? So SN2 style reactions, so we can use acetylides or just do an SN2 reaction with some sort of nucleophile. So gain is going to be some sort of SN2 alkylation. What about a loss? Yeah, usually ozonolysis. That's the only method we know of so far.
That's the only method we know of getting rid of carbon?
This is the only method we know of right now. We're going to be building up our chemistry toolbox as the year goes on. And you still need to kind of address, all right, what reactions do I know where I can add on carbons, and what method do I know where I can cleave carbons? But we're going to use some pretty cool reactions. These are just what we know now. These are the basics. All right, for step 2, we need to determine if the functional group is different. Usually it's pretty easy to tell, right? Yep.
On this, on the thing from the book, if you added, one of the ways to add a carbon was the NaNH2 and then the methyl iodine or bromine or something?
Yeah.
How come that's not?
Well, what's happening with methyl iodide? What sort of reaction is occurring?
We're adding a whole,
So it's an SN2 on the methyl iodide. So in this case, SN2 style reactions are typically used to install a carbon. So it's exactly that. You can use an acetylide, and that's what we've been using a lot of lately.
Okay.
All right, so our second step is to determine if the functional group is different. Another thing to pay attention to is whether or not that functional group is coming off of the same carbon or if it's moved around at all. I'll say or at the same or different position. So these are the 2 key points. We need to keep track of our carbons, and then we need to keep track of our functional group transformation and determine whether or not it's actually changed position on the chain. In order to do the second part, you really, really need to know your transformation reactions. And that's where I was telling you guys that flashcards and a lot of studying helps. The more you see these, the more fluent you'll be, the faster you can work through synthesis problems. If you're constantly having to open up your notebook, it's going to be a lot slower to work through these. So review transformation reactions. Like I said before, we've kind of developed a toolbox of these transformation reactions. The first one we learned about was substitution. which I think was chapter 7. Then we covered elimination, which was chapter 8. And then we did alkene addition, which was chapter 9. And then we did alkyne addition, which was chapter 10. And then we did radical reactions. A few people have asked me, well, what reactions do we need to know? A really good study tool for going through these transformation reactions is at the end of the chapter in the Klein textbook. They have a summary of reactions for the chapter. If you go through and copy that down and omit a reagent or a product and then have that answer on the back side of a flashcard, you can really quickly flip through those at the end of a lecture or before bed or when you're on the bus or any time like that. It's just small digestible study sessions are the best way to learn these. If you try to cram all night before an exam, it just simply doesn't work. Your brain gets saturated, you get tired, and you forget things pretty easily. So those are the main transformation reactions we need to know. It's kind of fun to think about because we've, in the span of 6 months, learned how to go between a variety of different functional groups. This last chapter, we saw how we can, oh man, come on. We can go from an alkane to a haloalkane. How can we go from an alkane to a haloalkane? So that's if we have an alkene, we can add a halogen onto it. But what about a regular alkane where it's fully saturated? Yeah, radical reactions, right? So in this case, we saw how to do this in chapter 11. And then we saw how to go from a haloalkane all the way to an alkene. How do we do that? Yeah, elimination. So that was, what was that? 8, chapter 8. And then we saw how we can go from an alkene, oh man, to an alkyne in chapter 11. And we're not just stuck going in the forward reaction, right? We saw ways where we can go from our alkene to our haloalkane. We saw that in chapter 9.
For the alkene to alkyne in chapter 11, are you talking about just radical reactions again?
From the alkene to alkyne? That's where we have our geminal dihalide and we react it with strong base. And it's similar to an elimination, but we saw it presented in chapter 11. We can also go from an alkyne to an alkene. What reagents would we need in order to go from an alkyne to an alkene? Yeah, poison catalyst or dissolving metal reduction. And we saw these in chapter 11. We also saw a way to go from an alkyne. Oh, man. Hopefully my pen's not dying here. And what chapter did we see that one, going from an alkyne to an alkane? I think it was chapter 11. And how do we do that reduction from an alkyne to an alkane?
Excess strong base.
Not quite. So if we have an alkyne, we just do a full hydrogenation, right? So just H2 and platinum. Alternatively, we can do that same reaction from an alkene to an alkane, and that was chapter 10. Is that right? Or chapter 9? Let's see, 7, 8, 9. Yeah, chapter 9.
Can you explain the mechanism again one time for going from an alkene to a haloalkane?
From an alkene to a haloalkane?
Yeah.
So if you have an alkene, you can react it with HBr, and it will add across, and we can do that Markovnikov or anti-Markovnikov. Alternatively, we can use elemental bromine and get that reaction to work as well. So we've got all of these reactions. Let's see if I'm missing any other.
What about the stuff we learned in
Chapter 10 was the, let's see, 7, 8, 9, 10. That was Alkane. Oh, shoot. These chapter 11 should be 10. Sorry, I'm losing track of these. All right, I need a pause here. I think it's my battery and my pen is dead. All right, I've got my battery fixed. Sorry about that. All right, so we saw this in chapter 10. Not chapter 11. Oh, my goodness. Yeah. It may be operator. All right, I'll fix this on the online notes, but for right now, my pen is not happy with this scheme that I've got drawn.
Which ones are supposed to be 10, right?
The 11s should be 10s.
The 11 should be 10?
Yeah, the chapter 11.
Except for the first one.
Except for the first one, going from an Alkane to a Halo Alkane. So this one should be a 10 as well. Sorry about this. Let's see if it works now. There we go. All right, so we've already covered a variety of different techniques to interconvert between all of these. I'm sure there are some others listed that I don't have on here, but the overall idea is we can convert between a variety of different SP2 or SP3 hybridized carbons at this point. All right, so now we're going to go back and talk a little bit more about retrosynthesis. And we talked about this a little bit already, but we're going to spend some more time on it. So retrosynthesis simply means we're going to work backwards through a synthesis. This is the way most chemists do it because it's a lot easier to work backwards than it is to work forwards and kind of chase your tail for a while. In order to do this, we use a special arrow system. So use these arrows to show that you're working backwards. Show working backwards. In this case, you can kind of think of it as being product is coming from this sort of starting material. Some people get a little sloppy and only show the one-way arrow, at which point it gets really confusing. You need to make sure you're using the correct arrow designation. All right, and then the next portion is to really focus on your functional group transformations. So that was the second part of what I was talking about on the last slide. Oh my goodness. I hope this isn't my computer. If only it were a Mac. All right, and in order to do this, we need to use our toolbox of reactions. The important thing to remember with functional group transformations is we may know quite a few different routes in order to form one functional group, but some of those routes might be dead ends for your synthesis. So it's important to remember that some routes may be dead ends. Maybe dead ends. But don't lose focus if you run into a dead end. Try to plan out a full line of attack with a bunch of options and then go from there. Sometimes it can save you in a pinch. All All right, so let's work through one of these problems together. And I'll show you guys how I would tackle this problem. And then I'll send you guys on your way to practice some more tomorrow. So we'll do that same small group synthesis activity that we did a couple weeks ago. And we'll be working with some fairly challenging synthesis problems. So for this alkyne, I want to show how you would make it from this alcohol. And so if we look at it, we can address the two things going on here. The first one was, did we change our carbons? Do we have new carbons or any carbons gained or lost? No, so we don't have to worry about that. So no carbons gained or lost. The other thing, too, is what's our overall functional group transformation?
Alcohol.
Yeah, we're making an alkyne, so. There are some times where these synthesis problems will trick you up because it'll have other functional groups, but primarily just focus on the functional groups that are changing when you're doing a retrosynthesis. You may have other functional groups just hanging out in the distance that don't do much. All right, so let's do our first step. So step number 1 would be addressing what ways do we know of to make an alkyne. Make an alkyne. Does anybody have ideas? Strong base. What would we need as our starting material if we're using a strong base?
We would need
A dihalide. So that was in chapter 11. There were 2 different dihalides that we could have used. There was one where we called it geminal dihalides, meaning the dihalides were coming off the same position. So we could have this guy, or we could have this guy, right?
And both would work equally, right?
Yeah, so let's take a look. If we react this first with NaNH2, that's excess, followed by water to quench it, we would get to our alkyne. And same with this one, we would also get to our alkyne using sodium amide and then quenching with water. There was one other technique we also saw from that chapter where we can have a monohalo alkene. So our last route would be to use this guy. Same idea, we do an elimination, NaNH2 followed by water. So we've got 3 different tools in our toolbox where we can make this terminal alkyne. So what we've got to do is assess the feasibility of each of these reagents. Yeah?
The last one, do you need it in excess?
In this case, you only need 1 equivalent. People normally overshoot those reactions on purpose. It helps drive it to completion. All right, so we've already established 3 possible routes we can start from. So now we'll do step 2. Step number 2. So assess feasibility of routes. So let's take a look at this first one that I left at the top of the screen. what ways do we know of that we can make this monohalo alkene?
That you start with an alkyne and use one equivalent
Yeah, exactly.
of like hydrochloric acid.
So if we have HBr, we can do that. Is that a very good route?
Yes, because it can only add into one side, right? From a carbon side.
Yeah, the route or the reagent is fine. It'll give us our product, but the problem is we're trying to make an intermediate to make a product by using our product as an earlier intermediate. So we're kind of chasing our tails there. So do you guys see? We're trying to use this in order to make our alkyne, but in order to make this, we have to start with that alkyne. So we're chasing our tails. This is what I mean by saying some routes are dead ends. You can write them down, and they work on paper, but the problem is you're just running around in a circle. You're not making progress towards the alcohol that we want as our starting material. So in this case, we can say that this route is a dead end. So in this case, we're not going to pursue that route any further because we know we're just going to be running around in a circle for a little bit. So let's take a look at the other route. What about if we have the geminal dihalide, where we've got two bromines right there and there? What method do we know of to form geminal dihalides?
Use access.
It's like, was it CL or BR2 and then carbon tetrachloride?
So in this case, we said we would need an alkyne in excess reacting with HBr. So this was another mechanism from our alkyne chapter. So we do Markovnikov addition twice.
I thought that was going into the carbon tetrachloride though.
That's with BR2. With hydrobromic acid, you don't need to use carbon tetrachloride.
BR2 won't work as well though.
The BR2, you would get tetra halogenation, not dihalogenation. So you get 4 bromines installed. So in this case, we've got excess hydrobromic acid. Again, the problem with this is we're at a dead end, right? Our starting material for this reaction is actually the product we want in the end, so this is not going to work either. So let's take a look at our last one. And we can say, all right, well, how can we get the vicinal dihalide?
You said our starting, what did you say about this one?
In order to get the starting material for this reaction, which is this
We
alkyne,
have to use that again.
yeah, we need our product in order to get this reaction to go, which kind of defeats the purpose, right? So in this one, we need to now assess, all right, how do we make a vicinal dihalide?
An alkene, yeah.
An alkene, all right? So let's take a look at the alkene. What reagent would we need?
Can you do BR2 here?
Yeah, BR2, right? You get 2 bromines installed. They're going to be anti to one another. I'm not showing stereochemistry right now, but we know that it's going to be anti. So in this case, success. All right, so now that we've done that, we just need to move backwards, right? All right, so step 2 was assess feasibility of a route. Step 3 is you want to repeat this. So repeat until you get to the starting material. All right, so now we have to ask ourselves, well, how can we make this alkene? What ways do we know of making an alkene?
Then we get to the round.
From an alkyne.
Yeah, so let's do the alkyne one first. Pretty quickly, you guys will see a trend here. What reagent would we need?
You could use
Yeah, dissolving metal, so I'll just put one of them up. Is this going to be a good route? Yeah, again, we're chasing our tail. This is a dead end. I like this problem because it shows you the potential of running into a lot of dead ends. And the more you work with these, the quicker you'll spot dead ends and say, wait, we're going back to the same functional group we were at before. We don't want to use this route. All right, let's do the next one. What's another way of making an alkene? You got to think way, way back, pre-Christmas. That was an eternity ago, I know. Elimination reaction, right? So I'm just going to abbreviate this LG for our leaving group. We need some sort of base as our reagent, right? And then we could do an E2 elimination reaction. So this goes all the way back to last quarter. And now we found success, right? At least we're making progress here. So in this case, the problem that was given defined the starting material, saying it has to come from that alcohol. So we're trying to work backwards until we get to the defined starting material. If I said you could start with anything that you wanted, you could stop at the alkene, or if I said it had to be 2 carbons or fewer, you'd have to even go further.
So we want to make an alcohol.
Yep. But now we found a way of having a leaving group that can pop off and form an alkene. So now we've got one last step. Where you want to show starting material going to first reagent. So the question we have is, all right, we've got this alcohol, but the problem is we know alcohols are poor leaving groups. Does anybody remember the, yeah, we have really only one good method to make an alcohol into a leaving group. And we discussed that in the elimination chapter. We said that this is tosyl chloride, which is abbreviated TSCl, and then pyridine. And by doing that, our leaving group becomes this really awesome tosyl chloride, which I always abbreviate as OTS. And now we've finally got our full reagent. If you're forgetting what tosyl chloride looks like, I'll show it to you briefly. So really what we're doing is we're doing a substitution where that chlorine's being popped off and we're turning our alcohol into an excellent leaving group. And then pyridine looks like benzene, but with one of those carbons replaced with a nitrogen. So I spelled it wrong, pyridine. All right, so the very last step is just put it all together. And I really recommend doing the full put it all together step because occasionally you will spot a mistake where you goofed up and did something wrong or forgot a carbon or something like that. And it's really quick and easy to check if you put it all together and double check. So the first step we had was to do tosyl chloride and pyridine. And when we do that, we turn our alcohol into a great leaving group. Now in our next step, we need some sort of base. Should I use something like sodium hydroxide here? Yeah, because it's a primary electrophile too, we would get some substitution. So we need a non-nucleophilic base. It doesn't really matter which one you use. I'll just say dBu, because we know that that one will only do elimination reactions. It won't do any substitution.
But we didn't do that in any of the steps above.
With the base? Yeah, we didn't pick a base at that point, but now we're putting it all.
Where did you say that at?
So for our step 3, I said we need some sort of base to do an E2, but we didn't clearly define the base because we didn't know what was going on with our leaving group. All right, so now we've got our alkene. We said in order to get our vicinal dihalide, we need Br2. And in this case, we know we're going to get 2 enantiomers out, but it doesn't really matter because we can carry them both on in the next step, which is NaNH2 followed by water. Oh, man, it's a sloppy arrow. All right, and now we've got our final product. That is our alkyne, and then we can high-five our partners that helped us with it. Oftentimes when you work in groups, they'll spot mistakes or problems that you get stuck on, and vice versa. You can help them get through a synthesis challenge that they're stuck on. So synthesis is really challenging. It's really important that you work with a group. Even if you've got it all figured out and you're really good at synthesis, I would still recommend working with a group because the process of explaining how you're thinking about it helps you to learn that information that much better, right? So the best way to learn is through teaching, oftentimes. We're going to briefly stop here, but I'll do a couple things. There's oftentimes multiple routes. If there are multiple routes, you've got to narrow it down to 3 different options. You can either base it off of time, so how long will it take you, or you can base it off of money, how expensive are your reagents, and the last one that people are increasingly using is greenness. Oh, I think it has 2 N's for my made-up word. So if there are 2 different routes that you can take, or even more than 2 different routes, you look at time, money, and greenness. Oftentimes they all overlap. Sometimes you've got to choose one over the other. But this is what industrial chemists have to do on a day-to-day basis. They can look at 5 different potential synthesis routes, and then they have to analyze it. They have to say, all right, is this going to cost the company a lot of money to make? Is it going to produce a lot of harmful byproducts? Or is it just simply going to take forever? They want to minimize it based on whatever they deem to be most important for that given reaction. All right, tomorrow is just going to be a practice day. I would recommend trying to start some of the sapling problems. It's all focused on synthesis, so it's a great review of the last few chapters.